All right, good afternoon. How is everyone today?
Pretty good.
That's good.
I am. Good,
Awesome.
I guess.
We're here, that's good. Um, all right, so I posted grades and comments for the midterm this morning, um, and listed what you got deductions for. I want to go ahead and go through the midterm and make some general comments on it. But as I mentioned in the announcement, a couple of things. One, I bumped everybody up 10 points to help offset the fact that it was, a pretty long exam and it was definitely challenging. And I think some people did run out of time. Um, so, put a little bit of a bump in there. Um, and the general overarching comment is, if you feel comfortable with what you were doing on there and you just think you ran out of time or maybe got flustered or something, that's okay. If you're feeling fundamentally confused about some of these things like truth tables and sum of products and stuff like that, we definitely want to talk as soon as possible because we're going to keep building on that stuff as we go forward, and you're likely to get more confused if those building blocks aren't in place. So you definitely want to come to office hours, tomorrow or office or lab hours next week, and let's figure out if there's something you're not clear on. Um, and any questions or comments before we just kind of go through the whole exam?
Can we talk about homework 5, or do you
Yeah.
want to go over the exam first?
We can do homework 5 first if you want.
Uh, I had a question about number 5 and how to find what the maximum frequency
Ah,
this machine
yeah.
could be clocked at. I was kind of confused there.
So this is different from the other questions. Um, the general setup is, we have our kind of generic state machine. And state machine has two main pieces, memory and logic, right? So this is our memory, which is also the state. And here's some sort of logic. But it's combinational logic. It doesn't have feedback in it. So basically, something comes in and stuff comes out. And some of the stuff that comes out feeds the input of the flip-flops that make up this memory, and some combination of flip-flop outputs goes into this logic. And we also have, some external inputs going into here. And we're not too worried about those. All right, so there's two things that affect how fast we can run this system. The first is when we set an input over here, how long does it take for the outputs to be valid? And that's the propagation delay. That's how long it takes, worst case, to get from an input change to an output change. So I think we call that, tau combinational logic. And let's just suppose that that's 75 nanoseconds. So there could be some combination of inputs that when I change an input here, it takes that long before the output is valid. So that's one of our timing factors. The other timing factor is the setup times for these flip-flops. Because you've got a clock coming in here, and it ticks, and it ticks, and it ticks, and it ticks. And we know from looking at flip-flops that before the clock ticks, these inputs have to be stable for a certain amount of time. So let's call that the setup time, tau SU, and let's suppose that's 25 nanoseconds. So if we look at a blow-up of the clock, if this is where the clock tick's going to happen, we know that for 25 nanoseconds prior to that clock tick, the inputs have to be stable. In other words, the things coming on this line aren't allowed to change. And we know that for 75 nanoseconds before this, the inputs to this logic have to be stable. So for this amount of time, these inputs can't change. Because if an input changes, you know, right here, it's possible that 75 nanoseconds later, which would be here, the output could change. And we're too close to the clock tick for that to be allowed. So any time prior to this, we can have the inputs change, not a problem. So what causes the change in these inputs? Well, that's the clock tick. Right? So the soonest the clock can be allowed to tick is 100 nanoseconds before the next clock tick. So we just figured out something that'll tell us the frequency of this clock tick. The time from one rising edge to the next has got to be greater than or equal to 100 nanoseconds in this case. Well, if the period is greater than 100 nanoseconds, then the frequency has to be less than or equal to 1 over 100 nanoseconds. And if you work this out, this will turn out to be 10 megahertz. So nanosecond would give you a gigahertz. 10 nanoseconds would give you 100 megahertz. 100 nanoseconds give you 10 megahertz. 1,000 nanoseconds, which is a microsecond, gives you a megahertz. So we can do this calculation separately in a minute, but this basically constrains, you know, this time from tick to tick has to be at least 100 nanoseconds, so the frequency has to be less than or equal to 10 megahertz. And it's basically the same calculation. This is just propagation delay of the combinational logic. This is the setup time for the flip-flops. And there's also a hold time, but the hold time doesn't really affect anything. The hold time just says we're not allowed to change the inputs too quickly after the clock tick. But if it's going to take, you know, a bunch of time for the inputs to work their way through this logic and come back around, we're not going to be violating the hold time in general. So mostly we ignore the hold time characteristic. And it's really just setup time and combinational logic. This calculation up here, this can get really trippy, but it can be really straightforward. And this will come up in 270. And it always causes headaches in there. But let's say this is 100 nanoseconds. Okay, that's the period. It's usually written as T. And it's the time from one clock tick to the next clock tick. If we think of a cycle, 1 hertz equals 1 cycle per second. And we can say 10 to the 9th nanoseconds per second. Or rather, 1 second equals 10 to the 9th nanoseconds. So hertz is a cycle per billion nanoseconds. And so 100 nanoseconds times 1 cycle is 10 to the 9th nanoseconds. Means 1 cycle is 10 to the 7th nanoseconds. And this is probably going to make it more confusing. Forget this. We'll grapple with it in 270. Let's just think of this. 1 second. Here's period, here's frequency. If your period is 1 second, that's 1 cycle per second. Right? If the time from here to here is a second, how many cycles do you make in a second? Exactly 1. So 1 second is 1 hertz. If it's 2 seconds from here to here, right, if that's 2 seconds of time, then in 1 second you're only going to have made half a cycle. So 2 seconds is going to be half a hertz. On the other hand, if your period is, you know, half a second, then if this is half a second, this is another half second, this is 1 second, how many cycles have you made? 1, 2. That's going to be 2 hertz. So if you keep this somewhere, on a piece of paper or a tattoo or something, right? It reminds you of how we go from period to frequency by taking reciprocals. And if you're working in seconds, reciprocal of period gives you frequency in hertz. And then everything else is just playing with units. But if I took this 100 nanosecond period and I wrote that in decimal, right, that would be 10 to the minus 7th seconds. And the frequency would be 1 over 10 to the minus 7th hertz, which would be 10 to the 7th hertz, which is 10 million, which is 10 megahertz. So that's an easy way to do that conversion between period and hertz. But I think in this course, this is the only time this comes up, is when we look at a state machine and say, how fast can you clock it? 270, we'll spend a whole week playing with timing, and we'll see this again. Does that make sense?
I like overclocking my computers anyway.
Yeah, well, no, overclocking can be fun, but depends how risk averse you are. So this system can run at some maximum speed, and if you exceed that clock speed, right, what can happen is, back to this example, we need 100 nanoseconds from tick to tick. We tick the clock, right, and the logic starts propagating through here, and if we tick the clock before 75 nanoseconds have passed, the outputs may not have even made it out through this block of logic. They certainly haven't gotten back around to set up the flip-flops. If we wait 80 nanoseconds, the outputs will come back through here, but they'll only have been stable for 5 nanoseconds, and bingo, we're ticking the clock. We're violating that hold time requirement. Sorry, that setup time requirement, right, which says these have to be stable for 25 nanoseconds. So what does a flip-flop do if you change the inputs within that setup time? It's unpredictable. Well, it's predictable, but it's effectively unpredictable. It might just cause a bad value. It could throw the thing into an oscillating state. It could open a black hole and suck us all in, but probably not. But we don't know for sure what's going to happen, right? So that's one danger. If we don't wait, even 75 nanoseconds, chances are this is just not going to change state. It's going to see the same values that it was seeing before, and your machine may look frozen. And then if you clock faster than that, right, then you start getting into issues of overheating and so on and so forth. What do you think happens if you clock slower than the maximum clock speed? If this thing needs, nothing faster than 10 megahertz, but I clock it at 5 megahertz or 1 megahertz or maybe 1 hertz, what's going to happen?
It might be more accurate.
Maybe. Almost certainly it's not going to do any harm, though. It's just going to be a really slow circuit. It'll probably take less power. It'll run cooler. If we weren't sure about these numbers, if 75 was really close to the actual propagation delay, on a hot day when things move a little faster, this might work great. When we come in the morning and it's really cold in the lab, this might not work at 10 megahertz. But if we brought it down to 5, it might work more reliably. But that's not the case for all logic, right? For flip-flops, that's totally fine. But a lot of microprocessors, there's a minimum speed you can run them at. And if you try to run slower than that, you can actually find that your system won't work. And that's because a lot of our computer systems don't use flip-flops. They use dynamic memory. And they use dynamic memory technology inside the chip sometimes. And you can find that, even though the fastest we can run is, some particular frequency, there's also a minimum frequency we can run at. And that's kind of a bummer sometimes. Because it's fun to run these things really slow. If you want to know how a microprocessor works, clock it with a push button. So you can actually step it one clock cycle at a time. And then you can go in and you can look at all the voltages and see the state of everything and so on, and then tick the clock and see what changes and so on. That's actually a lot of fun. but it doesn't work on some machines. All right, other homework questions since we're in the homework?
Actually, I have a question.
Okay.
I remember last second. So, on the lab, during that, so when I was writing up my schematic, I was just wondering, were we just supposed to write up a schematic for the adders and then implement it, with the decoder, or were we supposed to include the decoder and segment in the schematic?
So once you're writing the schematic, right? So you're doing equations up through step 3. Step 4, you're doing a schematic. So for anything that involves logic gates, ands, ors, XORs, things like that, you want to stick to the logic gate symbols.
Mm-hmm.
But when you get to something like, the 7-segment decoder, or for lab 5, when you get to the counter, what you can do is you can draw a rectangle. And don't draw a picture of the chip. Don't draw a rectangle with 14 pins on it, right? Make it easier on yourself. Just draw a rectangle, but show the pin numbers. So if I want the output of this to go to pin 2, right, just draw a wire into this box and put a 2 there. And label this, U5, and up here in your block say, whatever the part number is, and the power connection and ground, and so on. But just since we don't have a standard logic symbol for a decoder, just draw a rectangle, identify it, and then just show the pin numbers, right? So if this is going to come in on pin 7, and maybe we've got an output from pin 1 going somewhere, and so on and so forth. And that's fine.
I did this for both the 7-segment decoder and for the 7-segment display. I don't know if there's like an official standard for a 7-segment display.
7-segment display, I mean, you can draw this if you like, because it's fun to draw. But same thing, you could put pin numbers on here. The other thing you can do is you could label this as I don't remember what they're called on the data sheet, but you could label them with the name of the pins that are on the sheet. And so if you come in on pin 1 here, if that's like segment A, you could label that. And here's pin 3, which is segment B, and here's pin 2, which is segment C, right? So you definitely want the pin numbers there, because that's how you know where the wires go. But if there's additional information you can put in to say what these inputs do or these outputs do, you can go ahead and put that in the box also. And 7-segment displays are pretty standardized, right? It tends to more or less always follow that A, B, C, D, E, F, G going around like this, and then G in the middle. So you could label these inputs E, D, C, common, and so on. But definitely put the pin numbers on.
Will we get docked if we didn't put the 7-segment display in our wiring diagram?
How far did you list? Did you list outputs for the 4511?
I listed all the inputs and the pin numbers. I didn't list the outputs.
Okay.
Because I just assumed it was, A through G and whatever it goes into 7-segment display.
Yeah, I'll probably mention it, but yeah, I don't think I'll dock you for that.
Okay. Thank you.
But normally you would want to list that. All right, cool. Anything else? All right, well, let's run through the midterm. All right. Let's see. So question 1 was doing a binary arithmetic and working with 2's complement. The one thing I'll say here is if you're doing 8-bit 2's complement, you got to use all 8 bits. It'll generally affect your answer if you only use 5 bits or 6 bits or 7 bits. So even though the number 23 has zeros after, the 5th bit, list all 8 bits. Go ahead and write those leading zeros in. This is sort of the life of a computer. It doesn't, have the option of only using part of a page to store a number. It's always going to use 8 bits if it's an 8-bit register. And so the ways that we teach computers to do arithmetic using 2's complement and half adders, full adders, for example, we always want a fixed bit size. So same thing when we're doing this by hand. So so we start off, write the number 87 in binary. So you can, do the divide by 2 and write the remainders. I'm just going to do this kind of in my head. So it's going to be 64 from 87 leaves me an extra 23, so that's going to be 16 plus 7. So as an 8-bit number, this is going to be, 128, 64, 32, 16, 8, 4, 2, 1. So that's 87. And then part B says write negative 87 in binary. So we're using 2's complement. So 2's complement means to get the negative of a number, toggle all the bits, and then add 1. So I'm going to go over here and say negative 87 equals, and I'm going to write the complement, 10, 10, 10, 0, 0, plus 1. And there's negative 87. I don't know what I'm writing. 1, 0, 1, 0, 1, 0, 0, 1. Alright. Do you know the trick for finding 2's complement without doing this, by the way? I think some people do, because I saw some shortcuts. There's a shorthand way to do this. Anybody know that and want to tell us?
Is it the first bit is the negative of
9-bit.
Yeah, is it like I don't know how to describe it. So that would be negative 128 plus all the other.
Yes. Oh, so that's an equivalent way to do it. There's a even faster shortcut. So if you have a number and you want to write its 2's complement, start from the right and just copy the bits up to and including the first one. And then copy the opposite of the bits from that point on.
I always flipped all the numbers and then added 1.
Yeah, so that's the way that I prefer people do it, just because that's really what defines a 2's complement. But if you work it out, you can discover the shortcuts. So like the number 6 equals this. Negative 6 would be this. But the shorthand way is start from the right and keep all of your bits up to and including the first one. So if we have 0, 0, 0, 0, 0, 1, 1, 0. So we're going to keep this bit. We're going to keep this bit. But as soon as we found a 1, now we're going to toggle all the other bits. And it ends up giving you the same thing. But, if someone like offers you $100 to give them a 2's complement with your head, you can do it in your head like this. Keep all the bits up to and including the first one, and then toggle all the remaining bits. If you don't like that, don't worry about it. You can always do this. This is guaranteed to be right. But it's a nice little shortcut sometimes. Alright, so that's negative 87, and then we were asked to find 23. And we actually did it up here because 87 happened to be 64 plus 23. So this will be 16 plus 7. So there's my 7, there's 8, there's 16. I'm going to put those leading zeros in. And then it says calculate 23 minus 87 by adding in binary your answers from B and C. So we're going to add these together. We're not going to do any subtraction, but since this is negative 87, adding them should give us 23 minus 87. So now we do bit by bit addition, and 1 and 1 is 0 with a carry, 1 0 1 is 0 with a carry, 1 0 1 is 0 with a carry, and you got to resist the urge to just fall into a pattern. 1 1 0 is 0 with a carry. 1 0 1 is 0 with a carry, 1 1 0 is 0 with a carry, but then here we have 1 plus 0 is 1 with no carry, and then 0 1 0 is 1. So this is 23 minus 87. And with 2's complement numbers, you can always look at this first bit, and if that's a 1, you know your number is negative. If that first bit is a 0, your number is either positive or 0. It's not negative. So we got a negative number, which is good because this should be something negative. And then in part E, it says convert your answer here to decimal. So how do we do that? Well, we know this is a negative number, so let's find its 2's complement. And that'll give us a positive number. This will be the negative of whatever that number was. So if I think of x, you know, the number that we want to find here is this, then the negative of that would be just the complement plus 1, and I'll skip over actually showing the work here, but this is what I would get when I take the complement and add 1. And the 0 up here tells me this is a positive number. This is 1, 2, 4, 8, 16, 32, 64. So whatever this number x is, its negative is equal to 64. Well, if negative x is 64, then x is negative 64. And so this thing is the 2's complement representation of negative 64. And now if you actually calculate 23 minus 87, you'll find out, hey, that's what it should be. That's negative 64. So main issues I saw there, a few people weren't clear on the 2's complement, and so they were just using this most significant bit as a sign bit. That's what we call signed magnitude. Totally different thing though. Or, you know, putting a minus sign in front, which is what we do as humans. We basically, it's a signed magnitude. We say, here's the number, you know, 87, put a minus sign in front to make it negative. 2's complement is a totally different thing. It's different from what we do as humans. It uses this representation for negatives. But once we do that, we don't have to know how to subtract. We can just add negatives. And the other issue is not using 8 bits. And so if you do this with, say, 7 bits, your answer ends up being wrong unless you sort of fudge it by throwing in some extra ones. All right, question 2. People did well on this one too. So a circuit with 3 inputs, and it should output a 1 whenever exactly 2 inputs are a 1. So I think everybody got this right. And this is, you know, just another version of the same thing that we've been doing all quarter, which is start with a description of a circuit, write a truth table from that description. So exactly 2 inputs are 1. You want the output to be a 1, otherwise you want the output to be a 0. So there's your truth table. And in this case, write a complete SOP. So write out the min terms for each row where you have a 1. So I could say f of a, b, c. And so for sum of products, right, the min terms, we write a bar if there's a 0, we write b if there's a 1. So a bar b, c, or a b bar c, or a b c bar. And then writing it in compact form. So compact min-term form is just writing down the min-terms corresponding to each one. And you want to write this as, you know, whatever you call your output variable. You need to list the inputs in whatever order you're using them in your truth table. And the most compact way to write this is just sum 3, 5, 6. A slightly less compact way to write this would be M3, M5, M6. An even less compact way to write this would be to put in the plus signs. And the most uncompact way to write it would be to actually write out what those midterms are, right? But all 4 of these basically say the same thing. But we've got to list A, B, C, because if I wrote this down in a different order, if I did C, B, A, it would be different midterms, right? Well, maybe. Actually, in this case, it might come out the same. But in general, it'll depend on the order of these. So that's a sum of products, and then a product of sum is just writing down the max terms. But for the max terms, we're making a product. And we list the max terms where we want our output to be 0. So that's going to be 0, 1, 2, not 3, 4, and 7. And even though we're writing down the max terms where we have a 0, we don't put a bar over here or a bar over here or something like this. If you actually write out what these max terms are, you would see that this ends up being exactly a function that represents f. And if we were to write this out explicitly, which I didn't ask you to do, it would be, each of those max terms. So for max terms, we write our variable, if we have a 0, we write our variable with a bar on it if we have a 1. And each max term is actually a sum. So this would be A or B or C. And then max term 1 would be A or B or C bar. Max term 2 would be A or B bar or C. Max term 4 would be A bar or B or C. And max term 7 would be A bar or B bar or C bar. So that wasn't part of the problem, but just for completeness. But we do get to write max terms later on. Alright, so question 3, we were building. Oh yeah, and the other thing I'll mention with max terms we use an uppercase M. And it's a product of sums. The max terms are sums, so we take their product. So it's, dots between them or just side by side and uppercase M's. Alright, so question 3. One of the big challenges I saw was correctly filling in the K-map from the truth table. And maybe I should have broken it into quadrants or something, because 1s and 0s tend to look a lot alike when they're jumbled all next to each other.
Also, when you're in a frenzy for time.
Yeah. So let me just write down a copy of this. And I'll group it. So this was our f of A, B, C, D. And that's not a proper truth table, right? But if you've noticed by now that we do all kinds of things to take shortcuts in digital logic and more generally as engineers. So I'm, not writing down this left-hand side of the truth table because it's always the same, right? And so I'm keeping that in my head. But I'm just going to use this to fill in the K-map. So it's always worth labeling the edges. Most people got these correct. A few cases where, the 1-1 and the 1-0 were swapped. That's just something you need to keep track of and be careful with. And then we're doing a sum of products, so we want to write the ones in. Okay? So there's an order. If we go through, this truth table, A is 0, B is 0, C is 0, D is 0, that's this block right here. Okay, second row, A is 0, B is 0, C is 0, D is 1, A 0, B 0, C 0, D 1. That's this block right here. Okay? After you've done these enough, you start to notice this pattern, which is if I do my truth table in that order, the rows lay out like this: 0, 1, 2, 3, 4, 5, 6, 7. Then we jump down 8, 9, 10, 11, 12, 13, 14, 15. Okay? I don't want you to just memorize that and forget everything else. The reason that we put, that ninth row, the 1, 0, 0, 0, the reason that goes here is because A is 1, B is 0, C is 0, D is 0. Right? But as a consequence of that, we find this numbering that looks like this. And so with that, if we want to fill in the ones, we're just going to go through 0, 1, 0, 1, 0, 1, 1, 1. And then we jump down to the bottom, 0, 0, 1, 0. And then 0, 1, 1, 1. So there's our K-map of ones. And then covering, so saw a number of issues with covering these. So remember, when you cover, you want your rectangles as large as possible, but each side of your rectangle has to be either 1, 2, or 4. You can't have a rectangle with a length of 3. So I can't do like a 2 by 3 to cover all of these ones here. I can do a 2 by 2 to cover those. I could do a 2 by 2 to cover those. I can't do a 2 by 4 because I'd be picking up some zeros. So this is going to force us to use more than one rectangle sometimes. That might end up covering a 1 more than once. That's just what happens. So, when you see a cluster of 4 ones, right, get excited. That's a good chance to do a 2 by 2. So I would definitely do these as a 2 by 2. And there's some ones, and the only way I can pick those up is to put a rectangle around them, but make your rectangles as big as possible. Pick up a 2 by 2. And same thing over here. Now we're covering these ones, multiple times. This one is covered by 3 different rectangles. That's totally okay. If it helps you make a bigger rectangle, go for it. If it doesn't, don't. And then this one down here, our only option to cover this is to maybe come up here and pick up a 1 by 2. And if you happen to do, a 2 by 3 rectangle, your product terms won't make sense. So to find the product terms, you look at each rectangle and you see which things change and which things are constant throughout that region. So in this rectangle, A is a 0 in both rows, so we're going to have A bar. B can be 0 or 1, so we ignore B. C can be 0 or 1, so we ignore it. D has to be a 1. So that's not A and D. And then this 2 by 2 in the middle, A can change values, B is a 1. C can change values, but D is a 1. So that's BD. And then this 2 by 2 sort of to the right, A changes values, B is a 1. C has got to be a 1, and D can be a 1 or a 0, so that changes values. And then this rectangle down here looks like A is a 1, B can change values, C is a 1, and D is a 0. And another thing you'll notice is the bigger your rectangles, the smaller your expressions. If I had a rectangle with just one square in the middle covered, it would have 4 terms in its product. 2 ones, I drop down to only 3 terms in my product. If I have 4 ones in here, I'll drop down to only 2 terms in my product. If I manage to cover 8 squares, I'd have a single letter in my product. And if I happen to cover all 16 squares, I don't have any letters. It's either a 1 or a 0. Alright, so there's the product terms, so we can write our output function. And it's the sum of these products. So the order doesn't matter. But there's an SOP. Anytime that you write an equation like this, make sure it's got 2 sides. Something equals something. And for my output, make sure you list the variables that are the inputs to it. So f of a, b, c, d is equal to, you know, all of this stuff. And why is it f? Because, you know, that's the value in our truth table. So we're writing an expression for f of a, b, c, d. Alright, and then the second part was to draw a schematic. So I got to tell you right now, almost everybody is drawing their switches perfectly. And that has never happened. It's pretty rare by the end of 270 that most people are drawing their switches correctly. Everybody here is drawing their switches correctly. I don't know if that's a Tinkercad effect or just this class or what, but it's fantastic. Very, very few wiring mistakes with switches.
Just out of curiosity, why do you think that is? Like, why do you think people mess up kind of on the whole switches part?
I think this is just an exceptional class. I think people are just
Okay.
like really with it. There's so many ways you can wire a switch. There's like, you know, several different ways you can try to do it. And, you know, inevitably it's just whatever. But yeah, for a number of weeks now, when I've been looking at people's labs and such, your switches are perfect, which is really cool. So yeah, way to wire a switch. Take the input, pull it up through a 1K ohm, and then use a switch to optionally pull it down to ground. And that's what most people are doing. Saw 1 or 2 cases with multiple switches where people tried to share one resistor, and that doesn't really work. So if I had another input and another switch, and I tried to, you know, share one resistor between these, I've shorted my inputs together. If I close this switch, this point will go down to ground. That also makes this point ground. So you can't share a resistor. You need a separate resistor for each input. Other than that, everything looks perfect.
What if you have it the other way around, like a voltage is coming from the ground side, and then you have all the switches tied to ground at the end?
So this is one way that people have tried to make switches, and so let's run this through a resistor and put it to ground. On paper, it looks like this would work, and this will successfully deliver 0 volts or 5 volts over here. So in this case, right, with the switch open, this is connected to ground, this is a logic 0. If I close the switch, this is connected to 5 volts, that's a logic 1. So voltage-wise, that works fine. The problem is there are some electronic devices that if I take an input and I connect it to 5 volts, I'll blow it out. Right? It can't handle the potentially unlimited current coming in from, say, a power supply. And in this case, if we put a logic 1 in, it's going through a resistor, so it's going to cap off the current at typically 5 milliamps, if that's 5 volts. Now going to ground, we don't have to worry about that. But when you're putting in a positive voltage, we usually want to limit the current. The chips we work with in this class, they're pretty robust, but you know, fancier microprocessors and so on, that would potentially blow the transistors on the input. So we want to stick to that. But logically, that works just as well. Oh, the other thing I'll mention here is ground and VCC. So our symbol for ground is this. That's ground, which is 0 volts. And that's completely unambiguous. You're always going to see that. Occasionally, especially in older things, we sometimes saw this symbol for ground. But unfortunately, you sometimes see this symbol for VCC. So I avoid that. Anytime I draw ground, I'm going to draw this, and that's always going to mean ground. When you want 5 volts, either call it VCC or call it 5 volts if that's what the voltage is. But don't ever use this symbol or something that looks like that symbol for 5 volts, because it gets confusing. And there were some cases where I used this symbol for ground on the exam, and somebody took it to mean logic 1, which I didn't take off for. But that's always going to be ground. And then 5 volts, just call it VCC or 5 volts. That's probably the clearest. Anybody know what the other word for ground is? You'll see on like old schematics.
Neutral?
That is another one, yeah. So neutral. There's another term.
I've actually seen this one, I think, on an application I've been using to draw schematics, Earth.
Yep.
Yeah.
Which is really cool, right? Because how do you get a ground system?
Though, right?
Say again?
That's where it like actually goes.
That's where it actually goes.
Spikes.
Right, somewhere there's a big, usually copper pipe driven into the ground, and you know your grounded outlets in your building are probably connected to that. Now we have water pipes, and if your water pipes are made out of metal and they conduct, right, sometimes ground's just taken off of those. But you know, in a industrial building, there's a connection to Earth somewhere, and that's, you know, kind of the universal ground measurement. So that's why it's called ground, because it's, you know, the ground. All right, so schematic. I'm not going to draw up. Oh yeah, totally. Yeah. Yeah, especially if it's raining, I'll bet. So I don't think I need to draw the schematic for this, but let me just kind of start it. So, you know, and you can do this fairly mechanically. And, you know, let yourself be a little lazy. I don't know if I need C bar in here or not, but, you know, I'm just going to draw these. Maybe if I have pencil, I'll erase them, but, you know, on an exam, I'm not going to worry about it too much. So I need 4 products. I need B ANDed with D. So there's a product term. I need A bar ANDed with D. There's another product. I need A C D bar. And I need B C. And I'll be extra lazy here and just use a 4-input OR gate, but some people did, you know, 2-input OR gates, which is fine. Cascade them together. And so this is our output F, and run it through a resistor, run it through an LED. Watch the direction of the LED, so the triangle points in the direction current flows. So if this end is connected to ground, then your LED goes like that. Your resistor can go on either end. And then each of these switches needs to go through a resistor and get connected to ground. And I would actually label the switches instead of the wires. And so draw your other 3 switches, and there you go. And so this was pretty successful. Main issues I saw was, you know, either doing rectangles that didn't have, you know, a power of 2 length or height, or not doing as optimal a cover as you might have. So, you know, maybe just covering these two ones with a 2x1 instead of a 2x2, which gives you a more complex expression. Those were the main things on the K-map. And then on the circuit diagram, it was either not putting in the switches or the LEDs. Other than that, you know, minor typo here or there, everything seemed solid. So that was good. And that was about half the test point-wise, those 3 questions. So question 4, the multiplexer. And this is an exercise in faith, maybe, right? There's no rhyme or reason to this circuit. There's nothing that we've done that looks like this other than the homework question, which was sort of equally weird. But my hint up here, my suggestion was, you know, just follow the truth table, right? So we've got a 4-to-1 multiplexer. Here's what the multiplexer does. And we have inputs A, B, and C, and we have an output F. And if you start making a truth table, it kind of works itself out. So let me show you one way to think about this. Actually, let me pull this in. So let's put this over here. So so A, B, C. And to know what the multiplexer output is going to be, we have to know what the select inputs are, and we have to know what the inputs I0, 1, 2, and 3 are. So the select inputs, S1 and S0, well, those are really easy to write because S1 is just coming from B. So this is just a copy of whatever is in column B. And S0 is coming from C. So this column is just a copy of column C. So that tells us what the select to the multiplexer is. And then we also need to know what the values of I0, I1, I2, and I3 are. So let's just go ahead and write those. And we don't necessarily need all this information, but I'm just going to put it down, and then if I need it, it's there. So I3 is coming from what? It's coming from B. So this is another copy of column B. So I3 looks like this. I2 is connected to ground, so that's always a 0. And again, if you did a 1, I noted it, but I didn't take off. I1 is A going through an inverter, so I1 will be the opposite of whatever A is. So it's going to be 1 in these cases, and it's going to be 0 in these cases. And then I0 is just being fed from A. So it looks exactly like that leftmost column. And now we can write down what this output F by using the truth table. For a multiplexer. So if S1 and S0 are both 0, the output should be whatever I0 is, which is a 0, and that's going to happen here also. If S1, S0 are equal to 0, 1, then the output will be whatever I1 is. So I1 is a 1, and down here, I1 is a 0. And 1, 0, the output will be whatever I2's input is. Well, I2 is a 0 here, and it's a 0 here. And if S1, S0 are both 1, then the output will be whatever I3 is. Up here, I3 is a 1. Down here, I3 is a 1. And I messed up here. This is I0, should be a 1. Alright, so that's what your output function f is. And there's nothing about this that necessarily tells you ahead of time that's what it's going to do. But that's kind of the fun thing about multiplexers, is we don't have to, you know, do a sum of products and k-maps and all that kind of stuff. We can really just sort of set these inputs to whatever we want, and our truth table will mimic those. So this is, you know, a totally random circuit. But if you just go with the truth table, there's what the output function looks like. So I think that's all you had to do for this, was write the truth table. Question 5. So question 5 is a product of sums. And so we have f, and I didn't give you input variables here. I probably should have. I wasn't trying to be confusing. But since I didn't give you input variables, you have to make them up yourself. And you can call them whatever you want, and you can put them in whatever order you want. But let's see. 0, 2, 3, 4, 7, 8, 11, 14, and 15. So make a k-map and show an optimal covering of the zeros. So our usual setup. And again, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Or you can put these in a truth table and you can see what the values of the inputs are. So these are the max terms. This is telling me where my zeros are. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So that's where the zeros will fall. And then to cover those, well, this one jumps right out, right? This is a nice 4 by 1. And here's a stray 0, so we'll pick that up with a 1 by 2. This is kind of sitting by itself, so we're definitely going to pick this up with a broken rectangle. And this is sitting by itself, so we definitely want to pick that up with the 1 on top. And then we've got one stray sitting up here, and we've actually got a choice of 2 ways we can pick that. We could go like this, right? Or we could go like this. And those are different but equally good covers. It'll end up with the same number of AND gates, the same number of OR gates. So then you write the product term corresponding to each of these, and we did this on an earlier problem, but this rectangle, for example, A can change value, B can change value, C and D are both 1. So for max terms, if C is 1, it's not C. And if D is 1, it's not D. And those are ORed together. So that's the product term corresponding to that. For this little 1 by 2 over here, A has got to be a 1, so that's A bar. B has got to be a 1, so that's B bar. And C is also a 1. And I'll do one more, which is this broken rectangle over here. So A can be a 0 or 1. B has got to be a 0, so that's B. And then C and D are also 0, so that's B or C or D. And so on, and then you OR them together, and that gives you your, or you take the product, and that gives you your product of sums. So main issues there, other than missing one of these zeros, and they tended to get dropped on a few people's tests. So missing a 0, not having an optimal cover again, so make sure your rectangles are as big as possible. and as few as possible. Remember that when you're writing these max terms, right, if our variable is a 0, we write it without the bar. If it's a 1, we put in the bar. That's the opposite of a min term. With a min term, if it's a 0, we write it with a bar. Max term, if it's a 0, we write it without the bar. So that's flipped, right, like everything else between max and min. So those were the main things there. All right, and then true false, pretty good on these. You can build any digital logic circuit using only 2 input XOR gates, true or false.
False.
False, because
Use NAND and NOR.
You can use NAND and NOR, but not XOR. That's just the way it is. I spent, a couple of weeks when I was in my teens trying to build everything out of XORs, and you can't do it. There's no way to get a NAND out of an XOR. It just doesn't work. But NANDs and NORs, those are universal. So this one is false. Sum of products version always requires fewer gates than a product of sums. True or false?
False.
Yeah, I think everybody got that one right. And just write something that has a single 1 and a single 0 and 15 ones, right? So your sum of products is going to have 15 terms in it. Your product of sums will have 1 term. So that's definitely not true. You can implement any Boolean function using a 4-to-1 mux. That's true. Most people got that. I think everybody got that. That's definitely true. That was what we talked about with muxes. In a K-map, you need to cover don't cares at least once. That's false. You don't need to cover them because you don't care about them. And basically, if I have, a don't care sitting like right here, it means...
It's optional though, right?
Yeah, it means I don't care if that's a 1 or a 0. So if I don't cover it, I'm treating it as a 0. Well, if product of sums, I'm treating it as a 1. If I cover it or I don't cover it, that changes whether I'm treating that as a 1 or a 0. But if I don't care what its value is, I don't care if I cover it or not. But if I really wanted to get a nice 2x2 rectangle here, I could say, let's treat that as a 0, and bang, I'd have one rectangle covering all 4 of those. Right? But if it doesn't help me, I just won't bother covering it. So they're completely optional. So D was false. And then E, programmable logic devices can be used to implement a 2-bit adder. Yep, absolutely. I mean, you can basically use it to implement any logic circuit that you want. Alright, and then question 7 was playing around with programmable logic, and I think this was the point where most people ran out of time, partially because it was the last question, but also I think it's well, I don't know. But anyway, a number of people didn't have time to do this or didn't do it. And so this was the motivation for giving back points mostly. But if we wanted to write sum of products, so look at where the 1s are, and I tried to make not too many 1s in here. So F, again, make sure that you name your variables. So this would be like F of A, B, C, D. And so we've got 4 1s here, right? We've got this row down here. So that's A bar, B bar, C, D bar. And then we've got the next row, which is A bar, B bar, C, D. And then we've got this row down here, which is midterm 6. So A bar, B, C, D bar. And then we've got midterm 15, which is A, B, C, D. And then we've got lots of repeats, right? So for G, it's also using midterm 3. So we can repeat this expression. So it's going to be A bar, B bar, C, D. And it's got a 1 in row 15. And then H. And H, we have one new entry down here, right? So we've got midterm 1. So and then we've got midterms 2, 3, and 15, so it'll be the same as these. And then the fuse map, right, you can just treat each of these independently if you want, and that gives you a perfectly valid fuse map. But you can also notice that, you know, A, B, C, D is being used for each of F, G, and H. So I could make one row of my fuse map, set these fuses for A, B, C, D, and then I would take the output of that and I would use that for F, G, and H. And there's a lot of redundancy, so the line corresponding to midterm 6 appears in both F and G, or F and H, so I can use those, and so on and so forth. So you don't actually need 10 rows of the fuse map. You can actually get away with about 5 or 6 of them. But, you know, put in your X's over here for whichever rows you want, and then mark those over here to generate F, G, and H. Some people turned it into a problem and marked all 16 combinations over here for each possible midterm and then just picked those off, and that's totally fine too. Dealer choice there. And people who got to that mostly seem to get it right, but like I say, a lot of people just said they ran out of time there. So that was that. All right. So any other questions on any of that?
Nope, I'm good.
Okay. All right. Let's take 5 minutes, and we'll come back. We'll see if there's any other questions on Lab 4 or Lab 5, and then we'll talk more state machines. So let's take a 5-minute break, and then we'll come back. right. How's Lab 5 looking? I know some of you just finished Lab 4, but looking
pretty good.
okay.
Yeah, I haven't really started it because I'm still working on the homework.
Okay.
Plan
So
to get started on it tomorrow,
cool.
possibly tonight.
So I had one student who came in and got this thing wired up, and it looked good, and it counts up to 9, and then as it counts from 10 to 15, you expect the display to go blank. We learned that in Lab 4. But then the simulation seemed to freeze for a few seconds, and then it eventually rolled over and went back to 0, and then it stopped, and it wouldn't tick or count beyond that. And I don't know if that was something in their circuit or if it's actually a Tinkercad issue. But in general, right, you want to follow the lab as closely as possible and you know, design the circuit, implement it, test it. But if it's doing something really weird, right, you always have the option of reporting that in your lab, right? So observations, you know, the circuit counted up to 9. It then went blank as expected, but then the simulation froze, and then when it unfroze, it seemed to be stuck at 0. Now this doesn't mean, you know, you can totally skip the circuit and say, you know, yeah, I built it and it didn't work. That's my observation. But, you know, if you follow the lab and you think it should be working and it's not working and you can't figure out why, right? You know, aside from coming to lab hours, office hours, and working with me on it, you can put that into your lab report, right? And say, you know, this did not, you know, do what I expected, and I don't know why. And, you know, that can be your observation for that experiment. So it's not like you can't turn in your lab report if you didn't get the circuit to work perfectly the way that you were expecting it to. So that's a valid observation. And I honestly don't know at this point if there is something weird in Tinkercad that confuses it when the counter overflows or not. So just be aware that might be some weirdness in there. Other thing on here, make sure that when you hook up the counter, you set those 2 reset inputs to ground. So the ones that are got weird labels around like pin 2 and 3, make sure those get pulled to ground. Double check your wiring on the timer, and, you know, throw in some LEDs. Put in an LED on the output to make sure that this thing is ticking. Put some LEDs on the output of the counter on its way to the decoder, the 4511, right? So that you can see if the output of the counter is doing the right thing. Is it counting in binary? And then take the output of the 4511, hook that up to the 7 segment. And again, as we said in the beginning of class, you know, for boxes like the 4511 or the 555, right? You can just draw a box, put pin numbers on those, label what those inputs or outputs mean. Give it a name, put that in your component ID block. And you don't have to number these in the same order that they are on the chip. You don't have to have 1 through 4, 5 through 8, because then you have wires crossing all over the place and so on. And we're not drawing a picture of the chip. We're just using a rectangle as our symbol for the chip, because we don't have a standard symbol for a 555 or a counter.
So, I have a quick question.
Mhm.
It's general for labs, I guess.
Yeah.
For the continued experiment or
Mhm.
future experiment, that's what it's called. If we have a failed experiment, is that something that we should just report on and call it good? Like, we don't.
You mean if your
I
new
guess just-
experiment doesn't work?
Yes.
Um,
Or
yeah. I mean, if you come up with an experiment and you describe how to do it, but you don't get the result that you expect, yeah, I'd say that's okay. But, you know, from a marketing perspective, you could actually turn that around, like, you know, figure out what's wrong with this circuit. And that could be an experiment.
Gotcha.
So that's one way to go.
Thanks.
Mm-hmm. For the new experiments also, I'm going to ask that you try to think of them in terms of, you know, actual experiments, something you might do in Tinkercad or with a proto board, as opposed to, you know, write the truth table for this circuit, or, you know, take this equation you came up with and now write it as a product of sums. Those are good exercises to do, but they feel a little more like homework questions sometimes. Even though part of the lab includes, you know, experiments where, or parts of experiments where you're writing truth tables or equations or using K-maps, that's usually not the punchline of the experiment. The punchline is usually a circuit that's implemented, and you make some observations or you do some tests on it or something like that. So think about, you know, more from the hardware side than from kind of the homework problem side. But I'm seeing lots of good new experiments in the lab so far. So keep thinking about those. That's good, and it's really good practice for sort of, you know, thinking bigger picture about the stuff we're doing in these labs. So that's really good. All right. Any other questions in general on this whole state machine business, the analysis of state machines? So let's.
Is it good to like do the state transition table first, and then check your work in something, say like Tinkercad?
So for analysis, right, we're given a circuit, and if you were to build that circuit, you might be able to see if you were doing a good job. That's a cool idea. I haven't thought of that. It's probably a lot of work to do that, but that's kind of a cool concept, actually. In fact, we should probably have a lab like that, since we've got Tinkercad.
I've been using like this logic simulator called sim.io.
Okay.
So I will like do the state machine analysis first. Is it a mealy machine? What's the state transition table? What are the flip-flops doing? And then I go in, and since it's all just logic gates and a clock, I can build the thing and simulate. Okay, well, if I'm in this state and these are my inputs, I'm going to go to this state, and then I can check and see if it's
Okay,
correct.
that's pretty cool. Yeah, I would say in general, the more that you mess with this stuff, the better, right? It's well and good to do it on paper and get your homework done and turn it in. That's, you know, the first goal. But if you have the opportunity to dig deeper into it in any way, either through doing your own experiments or playing with other software or something like that, that's only going to help. And at the end of the course, when we're doing Verilog and hardware design language experiments, we'll see, you know, another way to create state machines using software, and that won't mean much to us unless, you know, we've gone through what we're going through right now, which is the low-level analysis and synthesis by hand. But yeah, that sounds like all good stuff. Yeah, we can talk mealy more machines again. So this is actually a really straightforward designation. So let's say we have a state machine, and it's got, let's say, 2 JK flip-flops. And let's say it's got, you know, some inputs, x1, x2, x3. And it's got some outputs, z0 and z1. Alright, and you're going to write equations for things, right? So what do you want equations for? You want equations for j0 equals, you know, something, k0 equals, j1 equals, k1 equals, and you want z0 equals and z1 equals, right? And the things in here will basically be some combination, in this case, of q0 Q0 naught, Q1, Q1 naught, X1, X2, X3. All right. This shows us the state, and our combinational logic generates these inputs and these outputs as some combination of the flip-flop outputs and the inputs going into the system. So to tell if you have a mealy or a more machine, you look at your outputs. And basically, if this expression contains any of your inputs, it's a mealy machine. And we can be a little more fine-grained about this. Let's just look at one output. Look at Z0. So if Z0 equals some function of, some variables, if the things that are in this expression for Z, if this includes X1, X2, or X3, then it's a mealy. Otherwise, it's a more. And we can think of each output as being a mealy output or a more output.
So, real quick, I've been doing research in the book and online about the difference between those machines, and it can be kind of thin. Like, if your input is going to through both your sequential logic, and it also talks to your combinational logic to affect a specific output, it would be considered a mealy, but it's only a more machine if it's only talking to the state,
right,
sequential part of your circuit.
Right.
Okay.
So presumably something depends on X1, X2, X3. Otherwise, they're just bogus inputs that don't go anywhere. And so almost certainly some of your state variables, your J, your K inputs, and so on will depend on these. But if you come up with an equation like, Z0 equals Q1, Q0 bar X1 or Q1 XOR Q0 or whatever, right? As soon as you see this, that's a mealy output. Right? As soon as you see any of your input variables, X1, X2, X3 in this case, in this expression for this output, that's a mealy output. If you don't see this anywhere in your expression, if this is all just dependent on, Q0, not Q0, Q1, not Q1, then it's a more output. Now, if all of your outputs are more outputs, it's a more machine. If all of your outputs are mealy outputs, it's a mealy machine. If it's some of each, then it's a combination. And when we draw our state diagram, we list each state in a circle, we write the state name. We can put inside the state any of the more outputs. So if Z1 was a more output, we could list Z1 down here, because it only depends on the state. But if we have things that depend on the input, we usually list the input, and then a slash, and then we can list the mealy outputs here. Because they depend not only on what state you're in, but also what the current inputs are. So it really just affects how we draw the diagram.
Is that how you prefer we draw the diagrams? More inputs inside the state, and then the inputs on the arrows?
Yeah,
the
that's...
outputs?
It's not horrible if you draw the more outputs on here, but it's not really correct. The more outputs really need to go inside this bubble. But the mealy outputs you cannot simply put in here because they're not just a function of state. Those have got to go on the arrows. There's something I was going to say a minute ago. Something that came to mind. And I think it's left my brain. Well, if I think of it, I'll mention it. All right. We've got about 20 some minutes. I know one thing I was going to mention. So we're putting in a little bit of a break on homework, right? So Lab 5 is still due Tuesday. That's on the regular schedule. But since I pushed the homework back a few days, I'm not going to give you new homework right now, right? We're starting state machine synthesis, presently, but we're only going to have a few minutes for it. So we're not really going to get into that until Tuesday. So next week, probably Tuesday, I'll post your next homework assignment, and you'll have a week to do that. So there's a few days in here where there won't be a homework assignment.
It still says that homework 6 is due next Wednesday.
Yeah, I'll change that because I haven't posted it, so just ignore that. Until you see homework questions listed there, it's bogus. But I will make.
I have a small question,
Yeah.
or maybe not so small question. And I know you've already moved on with topics. In my head, mealy will always need an input in order for it to basically have and run correctly. But what if you have an input like x, but during all your equations you realize that even though x is a factor, it doesn't ever affect anything?
Yeah, so then it would be like a Moore machine.
Cool. I was right.
Cool, awesome.
Thank you.
Yeah. Oh, I remember now the other thing I was going to say. So, there's a textbook for this course, and I'm more or less following the text, not necessarily in strictly the same order. We picked up a little bit of the later stuff out of order. But, this is another reference for the stuff that we're doing, including, all the stuff with product of sum of products, K-maps, and so on. Now, there's some stuff in here that we've skipped. The business of, prime implicants and some of that stuff with K-maps that I said to skip. Some of the stuff with compressing truth tables using K-maps, we skipped that. But, it's another treatment of the stuff. And for example, bunch of questions on half adder, full adder. Those are discussed in chapter 9, right? So, right? So 9.5 has a whole section on half adders and, truth table for it, schematic diagram for it, full adder, truth table, schematic diagram, how these things get put together to make a ripple carry adder and so on. So don't forget about the textbook, right? It's a really good source of information, and it's a different treatment. So this is written by Izad, and so same topics, different approach in some cases. And so the more approaches you have to something, the more likely it's gonna click. But a lot of the stuff that we've done has actually been from chapter 9, so multiplexers, demultiplexers, and so on. And then the rest of it is mostly from the beginning of it. One thing we do skip is we will skip chapter 5, I believe it is. Right, so we've been doing analysis of combinational logic, and we're going to get into synthesis. And so that's chapters 3 and 4, and then we're probably going to skip chapter 5, and we'll do sum of 6, and then we're going to go on to 7, and we don't do any of chapter 8. That's left over from earlier terms. All right, let's see. Now we got 20 minutes. Let's do some state machine synthesis. So this is really nothing other than taking everything we've been doing with analyzing state machines and just turning the crank in the opposite direction and trying to go from a state diagram to a transition table to a set of equations to a circuit. So it's running the process backwards. So let me make a totally random state diagram. And I'll just say state A will go to either B or A. State B, we can go back to A, or maybe go to C. State C, we can go to B or D. And state D, we can like stay in D or go back to C. And I'll make this a more machine. So there's our outputs. And so here's our key. So here's the state. Here's my output Z, and our transitions are driven by an input variable X. Alright, so that's a totally random diagram. I have no idea what it's going to look like or what it even does. But you know, mostly we move over to state C, and we can bounce back and forth between C and D if we put in a 1. We can go backwards from C too, so it does something. So how would we go about designing a circuit to implement this? So we have a sequence of steps.
Quick question.
Yeah.
I'm seeing that you're not putting the outputs, just the inputs on this. Are they required for this?
So I'm putting the outputs down here. So I'm making this as a Moore machine, so the outputs are only a function of state.
Okay.
Alright, but if we wanted a mealy machine, I could have an output, you know, Z2, and I might put /Z2, and then I'd list it on each of those arrows.
Oh, so you only do that with Moore's. Okay.
Yeah, with mealy machines, you list your outputs on the arrows because they depend on the input. And that's what these arrows show. For a Moore machine, since they only depend on state, I can actually list it with the state. So inside the bubble. And that's really the only difference we care about for mealy and Moore machines is how we draw the picture. The analysis and everything else is totally agnostic to which of those machines we have. So the first thing we need to know is what kind of flip-flops are we going to use? And you know, it may be given to you on a test or a homework. It may be that, you know, you live in JK flip-flop land and the only flip-flops in the world are JK flip-flops, so that's what you're going to use. It may be that you know, you don't know what type of flip-flops to use, and so you're going to build a circuit using every possible type of flip-flop and figure out which one takes the least circuitry, right? And this is something that, you know, software would do for you typically and so on. But in most cases, since we're doing, you know, homework questions and test questions and so on, you'd be told what kind of flip-flops to use. So let's start off with a relatively simple version of this, and let's say we're going to use D flip-flops. Okay. The next question is how many? So how many D flip-flops do you think we need to build a machine that will implement this state transition diagram?
Wouldn't it be 2 because it has 4 states?
It has 4 states, so if we use 2 flip-flops, 4 combinations of those outputs, 1, 2, 3, 4 states, that'll work perfectly well. But we could use more. We could, you know, totally lose our minds and say, hey, let's use 4 flip-flops. And there's no law against that. So I have 4 states, A, B, C, D. And the idea is if we use 2 flip-flops, maybe we'll do something like that. Right, so we'll use this combination to represent which state we're in. But you know, we could do something like this. And we could code our 4 states like that. And now, you know, I would not be allowed to have a combination where, for example, both of these were a 1. But, you know, if these were the 4 values in my flip-flop, that would mean state A. If these were the values in my flip-flops, that would mean state B. Now this takes more hardware. I'm using 4 flip-flops when I only needed 2, but sometimes we'll do this. And we'll come back to this later, but this is something called one-hot encoding. So hot is a kind of generic electrical term for voltage, something other than ground potential. So like the hot wire is the one that's carrying voltage relative to ground. So one hot encoding means that the way we've decided to encode our states, only one flip-flop has an output that's not 0 at a time. And this turns out to be really nice for handling glitches. Because when we move from, say, this state to this state, there's some potential ambiguity depending on how the different flip-flops change and when they change. Whereas from here to here, right, basically one flip-flop turns off, one turns on. So we'll play with that later, but you might see mention of that if you're looking in the book. So different ways that we can choose to encode. So we have to decide how many we're going to use, and usually we would want the minimum that we need, which in this case would be 2. So we'll do 2 D flip-flops. And so now we're going to make a table. And so our table starts off looking like it did when we were doing analysis. We have a state. And that state corresponds to a pair of flip-flop values. So I'm going to use this table right here. And we have an input, one input X. So I'm going to list X over here. And I'm going to spell out all the combinations. So state A, my flip-flops are 0, 0, and it could be my input is a 0. State A, my flip-flops are 0, 0, my input could be a 1. State B, my flip-flops are 0, 1, and my input could be a 0 or a 1, and so on. Alright, so there's my 4 possibilities. And at this point I can go ahead and fill in my output. All I'm doing at this point is I'm just taking this diagram, I'm transcribing it into a table. So my output only depends on the state. So if I'm in state A, my output's a 0. If I'm in state B, my output's a 1. State C, my output's also a 1. And state D, my output is a 0. So that's what my output's going to be. Alright, so this is all present state. And what this diagram is telling us is if my present state is A and my input is a 0, my next state is B. Everybody see that? If my present state is A, my input's a 0, my next state is B. That's what that arrow's telling me. So I'm going to make a column for, or a few columns for next state. So if my state is A and my input's a 0, my next state is B. If I'm in state A and my input's a 1, my next state is A. And so we go down and we fill in this table. State B and my input's a 0, my next state is A. State B and my input's a 1, I end up in state C. State C, 0 takes me back to B. State C, a 1 takes me over to D. And state D, 0 leaves me in D. And a 1 takes me back to C. And now I'm going to write this in terms of the new values of Q1 and Q0 based on what states A, B, C, and D mean. So state B is a 0, 1. State A is a 0, 0. State C is 1, 0. And state D is 1, 1. This is where it's really helpful to have your own conventions for numbering things. For example, I'm going to try to always do Q1, Q0 instead of Q0, Q1. I messed up once last week. But try to have a convention for yourself, because if I flip these around, or I flip these around, or I do these different from here, I'm going to get all tangled up. Right? So habits are your friend. All right. So this is all just transcribing what's in this picture. Now I can throw the picture away. Okay? I've got all that information in here. Now we have to start doing some flip-flop type engineering. We have D flip-flops. So we're going to have a flip-flop with a Q0 and a Q0 bar, and another with a D1 coming in and a Q1 and a Q1 bar. And we're going to build a circuit which is going to drive D0 and D1 based on the Q's and this external input X. So what we have to answer now is, what value do we want this D1 input to have in each of these 8 cases? And the answer is, we want D1 to have whatever value it needs, so that when the clock ticks, Q1 becomes each of these things. We want D1 to have whatever value it needs to have to make sure that Q1 takes on these values after a clock tick. Well, for a D flip-flop, this is easy. Because a D flip-flop, Q takes on whatever value D is. If we want Q to become a 1, easy, set D to 1. If we want Q to become a 0, set D to a 0. So again, just for D flip-flops, this column is going to be a copy of Q1. But I'm not just copying this down because that's what we did in class, right? I'm copying this down because this one right here says, you know, in this combination of states and inputs, when the clock ticks, I want Q1 to become a 1. Well, how do I do that with a D flip-flop? Set the D input to 1. Right? That's why this is a copy of that. And then similarly, D0 is going to be a copy of Q0. And now we're pretty much done with the state machine analysis part. Now we're back to, you know, the kind of thing we've been doing all quarter, the kind of thing we did a bit in 120. Write equations for D0 and D1, and for Z. So I skipped a step here, right? Make a table, and then decide on flip-flop inputs.
Would you also write the equations for the external outputs, or do we already know what that is?
Yes, you need equations for the external output and for the D inputs. Alright, so this step we did right here was step 4. Decide on the flip-flop inputs based on what you want the Qi to be, Q0, Q1. And then step 5, write equations for the flip-flop inputs and the state machine outputs. So in that case, that's the D's and the Z. So do your sum of products, product of sums, K-map, magic, whatever, and basically come up with D0 equals something, D1 equals something, and Z equals something. And then step 6, sketch your circuit.
Would you quickly go over why you went to it's a D flip flop?
Up here,
Yeah, I missed that.
totally
Is it
random.
because of the relationship between the two states?
So in the beginning of the problem, you're usually told what kind of flip-flops to use.
Oh, okay.
So you'd be told, implement this state diagram using T flip-flops or using JK flip-flops or D flip-flops. The reason I picked D is because it makes things a little easier when we get down to filling in this. And we probably don't
Are
have
we gonna
time.
have a problem with an SR flip-flop?
I won't give you an SR flip-flop question. You'll see them in the book, but I don't think people actually use SRs because they're like slightly hobbled JKs. And they have that funny undefined state when both inputs are 1. You should know what an SR does because other people will ask you. But, everything except when both inputs are 1 is exactly the same as a JK.
Is it used for like finding a random value? Because if it's 1 and 1, it'll give you something that we don't know.
It's usually to find what it will do, but it's not terribly meaningful. You look at the design for it, and it's either what's called set dominant or reset dominant, which says if you specify both, which one wins out. And it won't be random. It'll usually do one very specific thing, and it just depends how it's built. But I talk about SR flip-flops mainly because it's sort of a natural way to start developing the idea of a memory chip. But I don't think you see them. I don't think you can actually like buy them. At least not as they're not as popular as JKs for sure. All right, so your last step is to sketch the circuit, and you've got equations for D0, D1, Z. They're going to be combinations of Q0, Q1, and X, and you get AND gates and inverters and all that kind of stuff, and you put them together, and then you write it up. So you'd have 2 flip-flops, you have your Qs, you have your X coming in from outside, you run it through all of your gates and everything to generate D0, D1, and Z. You feed D0 back into here, feed D1 into there, Z goes outside, and the last thing you do is you take all your clocks, you connect them together, and there's your circuit. So we'll have to do this on Tuesday, right? This is just kind of a first view of the synthesis process, but it's really, analysis run backwards, right? And for D flip-flops, this is really straightforward because it's just the Qs, but when we look at Ts and then JKs, it gets a lot more interesting. And this is where we're going to see lots of don't cares popping into our truth tables, and we'll see why don't cares are really nice things to have in truth tables, because they make K-maps a whole lot more fun to do, because it's easier to cover. So we'll definitely Tuesday we'll go through a lot of examples of this in more detail, and we'll take it all the way to the end, including sketching the actual circuit, and that'll kind of close the loop on the whole, analysis, synthesis, forward-backward process. So we'll be doing that, next week, Tuesday and Thursday, definitely. That's week 7, and then we're up to week 8 the following week, and that's probably where we'll start talking about Verilog, and that'll be the take us through the end of the course.
Quick question.
Sure.
When do you think the next homework is going to be due? Just
A week from Wednesday.
wait for months.
Yeah, so I'll post it up next week.
And a half off.
Say again? Yeah.
So you're okay.
Yeah, so I'll probably post it on Tuesday, and we'll talk about it in class, and it'll be state machine synthesis questions, and those take some time, but I want to make sure we've actually gone through a whole example with a few different types of flip-flops before I expect you to start working on those. So yeah, a little bit of a break from homework. All right, cool. Thanks for sticking around. A few extra minutes. Have a good rest of the day, and I will see you next time.
Thank you.
Thank you.
Thank you. See you.
You're welcome.
Thank you.